Hey guys, welcome to this video on determining the direction of the electric field, where we're going to get into a little bit more detail about vector fields and field maps so that we can see visually how electric fields work. Two quick notes. First, make sure you've watched the introduction to the electric field video and also the calculating the magnitude of the electric field video so that this one will make more sense. Also, I record these a little bit slower just to make it easier for me to write and explain some things, so I always recommend you watching it played back at a slightly faster speed if that works for you. Alright, so when we talk about the direction of the field, what the heck are we actually talking about? Well, we talked about the fact that the electric field quantity is a vector quantity, which means that we have a value of magnitude or strength to the field, but we also have a value of direction or orientation. Now, if you think of velocity as being a vector, you know that you could have a speed value, which is the magnitude, but you can also have the orientation or direction of the velocity, which at any single time is always just pointing in the direction that you're moving. So how does an electric field then have an orientation or a direction? Well, that's what we're about to get into. Just a quick reminder here, when we're talking about these terms source and test charge, it's extremely important for us to make sure that we are all on the same page. So I'm just going to quickly point a couple things out here. Remember that this uppercase Q is the source charge. That's the object or the charge particle that is creating the electric field, whether there is a test charge there or not, or a little thing to experience the field, and that's this one over here. So I usually will use uppercase Q for source charge, lowercase q for test charge, but really they're the same thing. All right, so because we're talking about directions and vectors, what I've done here is I've made two traditional Cartesian planes, and I placed my little source charge here in each example at the origin. And what I'm going to do side by side here is deal with, well, if we have a positive source charge, and what happens if we have a negative source charge, just so that it makes a little bit of comparative sense. Because some of this stuff is conventional, which means that it doesn't necessarily have a very logical reasoning anymore, but that's how we set it up and that's how we use it. So let's jump right into that part of things. The source charge is going to create a field. So if I place any test charge in its vicinity, we will know what's going to happen to it. And it's going to describe what the electrostatic force will be on that little test charge at every location. Well, when a lot of the beginnings of electrostatics were being formulated, most scientists assumed that test charges could only be positive. And we know that's not entirely true. In fact, most of the moving charges are electrons, which have negative charges. But we're going to assume, in order to create our convention, that test charges are positively charged. And what the field looks like, or the direction of the field at every location in this space, is really telling us what direction would a positive test charge move if it were placed at that location. So I'm going to say that one more time because that's the crux of this whole thing, is the direction of the electric field, or what the field looks like, is a set of arrows that tells me what direction would a positive test charge move if it were placed at any location within the space around the source charge. So remember, the convention, the direction of the field, is always determined by where a positive test charge would move. Whether it's a positive source or a negative source, that doesn't matter. It's always the direction that a positive test charge would move. So here's what I mean. Over here, all the coordinates on this map represent locations. And you want to think of the source charge here as just being a point at 0, 0. So I've shown it extended, but it doesn't really occupy all that space. So for example, if I were to place a positive test charge at this location here, 0, 1, what direction would it get pushed? Well, we know that if you put a positive charge near a positive charge, it would get repelled. So it's going to get pushed in this direction, away. Okay, let's pick a new point. If I were to place a positive test charge at the location 1, 0, what direction would it get pushed? gets pushed outwards like this. Subsequently, we can put in all of these other ones here. And you may notice that what I'm doing as well is I'm also making the arrows, well, I'm trying to make the arrows the exact same length if they're the same distance away from the source charge. So over here, all my arrows are the same length. Well, that's really telling me the length of the arrow here is telling me the magnitude of the field. So the length of the vector or the arrow, which I'm just going to put here vector, the length of the vector tells me the magnitude. Now, the direction of the vector is what direction the arrow is pointing. So what its orientation is different depending on what location you're at, but the meaning is still the same. Now let's go ahead and draw what the field's starting to look like, if you will, for a negative charge. Again, the convention says that we always use a test charge, which is a thing that we're testing the field with. That's where that term comes from, but we're going to do it for a negative source charge. So if I were to place a positive test charge at this location right here, it's no longer going to have a direction pointing away because I know that positive charges are attracted to negative charges. So I'm going to draw the arrow pointing towards it. Same thing would happen at all of these locations. If they're equidistant, they would have an equal length arrow pointing towards the source charge. So we can see that the convention always is determined by positive test charges. We'll make a quicker statement here in a second that we can use all the time without having to go in and draw every single point. What if I picked a point over here? Let's say I'm going to choose a different color here so I can represent it differently. If I were picking now this point here, 0, 2 away, the only thing that's going to happen is that the length of the vector, the magnitude, is going to decrease. So it's going to get shorter, and it's actually going to get shorter by a squared amount because these are inverse squared proportion. But either way, the arrow is going to become a lot smaller, but it's still pointing away because the little positive test charge would still move away if it was placed at any of these particular locations. And so what I'm seeing is that the direction of the field has not changed. All that's happening is the field is getting weaker as I move away. And you could think about this, the further I move away, the shorter this little arrow would get, and that would represent that the field is getting weaker. So when I draw a vector field, what I'm trying to show is that at every location in space surrounding the source charge, what is the strength of the electric field visually? So the arrows represent how the field looks based on how strong it is, using arrows as the representation of the field. So when you think about this, does an electric field actually look like something? Not really. It's kind of like the wind. The wind doesn't really look like anything, but we can see its effects, and the direction that the wind blows things tells us what the wind looks like, if you will. So it's the same kind of idea here. You just have to remember that the reason that the arrows are pointing away from the positive charge and towards the negative charge are because test charges were always assumed to be positive. So the rule now, the convention, is that if you have a positive source charge, your arrows will point away from the positive source. If you have a negative source charge, the arrows will point toward it. And that's the convention now. So you don't have to go to every point and think about it. If I gave you a positive test charge and you wanted to draw the electric field lines, you could literally just say, yep, the field lines point away from this positive charge, and that would be good enough. Now, the last thing that we're going to discuss here is how do you go from a vector field, which shows all these little individual arrows, to what we refer to as a field map. The way I like to think about it is that the vector field is the more specific, whereas the field map is less specific. So what the field map does essentially is it takes all those vectors and just connects them. So right now I can see that the field is getting weaker as I move out because the arrows are getting shorter. Well, the field map's not going to be able to show me that, because what the field map does is it just draws a straight line like this and says, well, that one's not very straight. It draws a straight line and just says that the field points in this direction. So it's not really telling me a lot of information about the magnitude of the field if I just look at it in the same way. It's just kind of showing me that the direction of the field is radially pointing outwards. So how does a field map show you the relative strength of the field? Well, the vector field diagram shows me that the field is stronger where the arrows are longer. The field map shows me that the field is stronger where the field lines are closer together. So when we talk about field maps, we are talking about field lines rather than vectors. And when we're talking about vector maps or vector fields, we're talking about actual vectors or arrows that are representing the strength of the field. So what we say that is, when the lines are closer together, the field is stronger. Where the lines are closer together is where the vectors are longer. So you can see that if all these arrows converge at this center point over here, that means that they are closer together here than they are further apart or further away. And the same thing would happen with the negative in every sense of the word. So just remember, when you're looking at a vector field, you have a bunch of lots of little arrows of different lengths. The lengths of the arrows tell you where the field is stronger. So in regions where the arrows are longer, that means that the field is stronger. For a field map, because we only have long continuous lines, we say that the field is stronger where the lines are closer together. So if I were to give you something that looked like this, we're going to assume that these are horizontal straight lines. Not able to draw those very well, but if we were to look at something like this, because these lines are neither getting closer together nor further apart, these field lines would show an electric field that is uniform. It's not changing as we move away. However, if I was going to show you something that looked like maybe like this, we could say that this region over here is a stronger electric field than this region over here, because this region's lines are closer together than this region's are. When would you use a vector field versus a field map? Well, that just depends on the kind of information that you're trying to get. Primarily in the rest of this series, I'm going to be focusing more on field maps, because we're not going to get into as much definition of vector fields. That would be something that you would have to have a lot more calculus, specifically Calc 3 or multivariable calculus. And that is not what I'm going to assume making these videos. So I hope that helps make sense of what the difference between the vector field and the field map is, and how we can see what the direction of a field looks like, or what a field looks like as a whole around some sort of source charge. In the next video, we're going to take a look at, what if you have more than one source? What would that do?